Okay, welcome back, guys. We just finished reconstructing these polynomials when we were given their zeros in their respective multiplicities. So we're going to kind of continue doing this, but I want to go over a property or talk about the nature of some zeros. Okay. If you notice in example 1, these were all integer zeros, okay? But in example 2, one of the zeros was an integer, but the other two were purely imaginary numbers. Well, if you noticed, these are opposites. They come in pairs, and we call those pairs conjugates, okay? And that's what these next two theorems kind of tell us. If we have any non-real zeros, okay, so basically that just means a zero that has an I, okay, so it could have a real component and an imaginary component, or it could just have the imaginary component like we saw with the 3i and negative 3i. This just says that they come in conjugate pairs, okay. So if a plus bi is a 0, then a minus bi has to also be a 0 of the polynomial. Let me give you an example. Well, if the a part is missing, then you just end up with purely imaginary zeros, and they come in pairs, okay? But if the a component or the real component is there, then an example might be something like this. 2 plus 3i would be 1, and then 2 minus 3i. Okay, so these are both non-real. And then the second theorem says that your irrational zeros will come in pairs as well, or conjugate pairs. Now, an irrational number is a real number. It's just one that involves a square root. Okay, so you've probably seen this before. When you were solving quadratic equations, you put a plus and minus and then a square root, and let's say there's a 4 under there, so you end up getting both a positive and a negative 2. That's kind of where this is coming from, okay? So in an instance like this, the a part would be missing, the c would just be an understood 1, and then b, of course, would be, oh well, that wouldn't be, this is not irrational. Let me change that 4 to a 5. Okay, and you'd have positive square root of 5 and negative square root of 5. If a and c are in there, well, c will always be a 1 for one thing, but an example might be 2 plus the square root of 3 and then 2 minus the square root of 3. Okay, so these always come in pairs as well. So basically, anything with an I and anything with a square root, they come as conjugate pairs. All right, now having said that, let's look at example 4. So it says, suppose we have a polynomial function of degree 4 with rational coefficients, and it has the following. I didn't really made a mistake here, but it has the following given numbers as zeros. So it lists 2 of them, and look at the nature of these. One is non-real, and the other one is irrational. Okay, so there's only 2, but this is a 4th degree polynomial, so we know there's 2 more zeros. They don't tell us because we're going to be using these theorems up here to figure out what the other 2 zeros are. Well, if 1 plus the square root of I is a 0, then its conjugate would be 1 minus the square root of I. And similarly, if 5 plus the square root of 7 is a 0, then 5 minus the square root of 7 must also be a 0. Okay. Alright, now it's okay, yeah. Now let's take a look at example 5. So suppose we have a polynomial function of degree 3. Oh no, I copied it right. I'm just misreading it. It says, suppose a polynomial function of degree 3 with rational coefficients has the following given numbers as zeros. Find the other zeros. Okay. Well, 5 is just an integer, but this 0 right here, 2i, this is non-real, so we know it's going to have a conjugate. And its conjugate will be negative 2i. And so now you can see we have a total of 3 zeros. Okay. And then example 6. Find the polynomial function of lowest degree. Now notice here, this one said suppose that we have a polynomial function. Find the other zeros. Well, we can do that by just looking at this because we know the nature of some of these zeros. This one, however, goes back to those first 3 examples where it says find a polynomial of lowest degree with rational coefficients that has the given numbers as sum of its zeros. So in other words, what example 6 wants us to do is what we did in part 1. It wants us to reconstruct or construct that polynomial that has these 2 zeros. Okay. Well, if these 2 are zeros of the polynomial, we know by the nature of these zeros what the other 2 zeros are going to be. And I'll list them. Negative 4i will be a 0 because it's the conjugate of 4i, and then furthermore, negative square root of 3 will be the other irrational 0. Okay, because those are conjugates as well. Alright, so we know we've got 4 zeros here. Now what we need to do is construct the factors because we know that the zeros come from the factors. And then once we know what the factors are, we can multiply them and we can reobtain that polynomial. Now this evidently is going to be a 4th degree polynomial because we have 4 zeros here. Alright, well let me list these factors. So x minus 4i will be 1. X plus 4i. And then x minus square root of 3 and x plus the square root of 3. Okay, so these are my 4 factors. And now I need to multiply all these together. So a tip here, guys, or recommendation would be multiply your 2 factors that corresponded to your 2 imaginary zeros first, then multiply the 2 factors that correspond to your 2 irrational zeros next, and then multiply those 2 binomials. Okay? The reason we're doing it this way is because these are conjugate factors. When we multiply these 2 binomials, the middle terms are going to cancel. Okay, so x times x is x squared. X times 4i is 4ix, but then negative 4i times x is negative 4ix. And finally, negative 4i times 4i is negative 16i squared. Again, those 2 terms in the middle will be 0, and so we'll have left x squared. Remember that, and I'll put this in the notes, I squared is equal to negative 1. Okay, So really, anytime you multiply a negative times I squared, it's like you're multiplying two negatives. So that's just going to become a positive 16. Okay. All right. Let me scoot these two factors over so I've got enough room. Because now I'm going to multiply these two together. Okay. Well, these are conjugates as well. So again, those two inner terms, or those two middle terms, are going to cancel. So x times x, well, that's x squared. X times negative 3, or x times negative square root of 3 will be negative square root of 3x. And then right here, the square root of 3 times x will be positive. And then the square root of 3 times negative square root of 3 will be negative square root of 9. So again, those two middle terms cancel. We'll be left with x squared. The square root of 9 is just 3, so x squared minus 3. Okay. So having done it this way, my last step is to now multiply these two binomials. So doing it this way works out better, guys, because you don't end up with any trinomials or anything like that. All right, so I'm going to bring this over here. Okay. And now I'm going to multiply these two. So x squared times x squared is x to the 4th. X squared times negative 3 will be negative 3x squared. 16 times x squared will be 16x squared. And then 16 times negative 3 is negative 48. Combine those two terms in the middle. You're going to get a positive 13x squared minus 48. Okay? And that is our polynomial. And it is a 4th degree polynomial, isn't it? Interestingly, if you were to graph this one, because two of the zeros are purely imaginary, you won't see those on the x-axis, but the square root of 3, the positive and the negative, you will. The square root of 3 is about 1.7. Okay, so you would see the function cross the x-axis at around positive 1.7 and then around negative 1.7. So, all right. You know, I think I had thought about stopping here, but I think I'm just going to continue. All right, now what we're going to focus on for the remainder of this section is finding all of the zeros of a polynomial. And we've spent a lot of time on this throughout the course, okay? But what we're going to be using synthetic division in facilitating this, and you're going to see how here in a minute, okay? Well, let me remind you of something. Whenever we did synthetic division, you know, I don't have 8.3 pulled up. Let me get it real quick. I was showing my other class this today. Oops. Notice, wait a minute. Oh, this one right here. No, this one. Yeah. Yeah, because I remember you even asked my class. So it says, using synthetic division, determine whether the numbers are zeros of the polynomial. Okay. So we had a row that corresponded to the coefficients of this polynomial. And we tried 2, and I did the synthetic division, and I got a remainder of 0. Well, that tells me that 2 is a 0 of this function right here. So if 2 is a 0, then the factor that corresponds to that is x minus 2. And then this that we have down here, I didn't mention it at the time, but these are the coefficients that correspond to the other factor. Okay, because 2 was a 0, this factor x minus 2, and this other factor, if you were to multiply them together, would give you back this original polynomial. Okay, you may be wondering, why am I telling you this? Well, because when we ran 2 through here, it's like we were dividing it by a linear polynomial. And so the quotient down here, this would be a third degree. Okay, so I can use this synthetic division to verify whether a number is a 0 or not. And if it is, I can take that new quotient that's down here at the bottom, and I can see if I can find the zeros of it. Okay. Sometimes I'll use synthetic division, sometimes not. You'll see why here in a minute. So anyway, we're going to start out, well, if you look here at my notes, we're going to start with polynomials for which a 0 is already given to us. Okay. And we're just going to verify whether it is or not using synthetic division. And then if it is a 0, then those numbers that we have at the bottom, they represent the coefficients of the quotient, and the quotient will be the other factor. And then if we can find the zeros of that other factor, then we can find all of the zeros of this polynomial. Okay. Now I'm looking at this polynomial right here, guys. We can see that it's a cubic polynomial. Okay. And it can actually be, you can find the zeros by factoring it. I just want to point that out. Factor by grouping, you could find all those zeros. But we're going to use this different method because most of the polynomials in the real world cannot be factored. And a lot of the polynomials you're going to see in this section cannot be factored. Or, well, they can be factored, but we haven't studied any techniques to factor like a fourth of some of these, maybe fourth degree polynomials. And so we're going to have to use this method here. Alright, so what I want to do is just verify whether -5 is a 0 of this polynomial or not. Okay, so the polynomial is already in descending order. There's no terms missing. So I can go ahead and list those coefficients. Okay, I'm going to use synthetic division the way we did in 8.3. Remember, drop down your first number, then you start multiplying and adding. -5 times 1 is -5. 5 plus -5 is 0. -5 times 0 is 0. -2 plus 0 is -2. -5 times -2 is +10. And in fact, we get 0. Okay? So not only does this tell me that -5 is a 0 of the polynomial, it also tells me that x plus 5 is a factor. And furthermore, it tells me that the quotient that these numbers correspond to down here is another factor. Okay, so this was originally a cubic, so these will be the coefficients to a quadratic. So 1x squared, there will be no x term because that coefficient is 0, and then -2. So in other words, the other factor is x squared minus 2. And it's a quadratic factor. So what I can do now is we can always find the zeros of a quadratic, right? I can use the quadratic function or the quadratic formula. So I'm going to take this quadratic factor and I'm going to set it equal to 0 and I'm going to solve it for x. But you can use the quadratic formula if you want, guys. I'm just going to solve it directly for x using the square root method. So I'm going to add 2 to both sides. And I'll get that x squared is equal to 2. And then if you remember, here again, we see that we have conjugates right here because the square root of 2 is an irrational number. Okay, and so this is going to give us that x is equal to the positive square root of 2 and the negative square root of 2. So that's why those irrational zeros come in conjugate pairs. And so anyway, these are the other 2 zeros of this third degree polynomial. The zeros are, I'll list them here, x equals -5, that one was given, positive square root of 2, and negative square root of 2. Okay, all of these are real numbers. So this third degree polynomial, this cubic, will cross the x-axis at all of these values. The square root of 2 is about 1.4. Okay. Let's go ahead and why don't we save example 8? Okay, we've got enough time to do it. I just kind of want to use it as a refresher before we tackle this last little section here. Okay. One thing I can tell you about it, though, we want to find all the zeros. One of them is given, but really 2 are given because we know these come in pairs. We use synthetic division to verify that they're zeros, and at the end we'll be left with a quadratic factor from which we can extract those last 2 zeros. Okay, but let's save this for the next one.